Hi everyone, this is Tim with a brief announcement before we get to our pre-lab lecture for experiments 4 and 5 this year. When we were looking at the schedule of the lecture versus the schedule of the experiments, we realized that it would be in your best interest, in order to have as much time to learn stoichiometry before you did the experiment on that. So what we've decided to do is we've decided to move the stoichiometry paper experiment to be experiment 5, and the empirical formula experiment of copper sulfate to be experiment 4. Unfortunately, we already printed the lab manuals, so we can't reflect that change in the lab manuals because there's simply too many of them ordered in order to reorder all of them. But we have changed it on the syllabus, which you can find on Blackboard, and the experiment schedule also found on Blackboard. So please make sure you're following the experiment schedule and syllabus on Blackboard, not the lab manual, because we're going to do experiment on finding empirical formula as experiment 4, and we're going to do the stoichiometry paper lab as experiment 5.
In this experiment, you're going to determine the empirical formula of copper 2-sulfate pentahydrate. Furthermore, you're going to look at the accuracy and precision of a classic general chemistry experiment. Before looking at the empirical formula of copper 2-sulfate pentahydrate, let's talk about empirical formulas in general. We're going to look at the empirical formulas for covalent and ionic compounds here. In the example of a covalent compound benzene, which I know is covalent because it contains no metals, it has 6 carbons bonded to each other and also bonded to 6 hydrogen atoms. This discrete unit in benzene has a molecular formula C6H6. The empirical formula for any compound is the simplest ratio of moles. You'll notice that for every 6 carbons there are 6 hydrogens. The simplest ratio is 1 carbon to 1 hydrogen, so the empirical formula is CH. In another covalent compound, glucose, which again contains no metals, therefore I know it's covalent, the molecular formula is C6H12O6. In this case, there's another common denominator of 6, and the empirical formula is CH2O. For some covalent compounds, like for example water, the empirical formula and the molecular formula are the same, because it happens to be the discrete unit is the simplest ratio of moles. In the case of water, there's 1 oxygen for every 2 hydrogens, so the molecular formula is H2O, and the empirical formula is also H2O. Ionic compounds are a little bit different. Here's an example of sodium chloride. Here, the purple balls represent sodium, and the green balls represent chloride. You'll notice that it exists in a large crystalline lattice, where every sodium is surrounded by chlorides, and every chloride is surrounded by sodiums. In the case of ionic compounds, the empirical formula is generally what is used. So this isn't Na100, Cl100, it's simply NaCl, the simplest ratio between Na, sodium, and Cl, chloride. At this point, you may be asking yourself, why would anyone want to use empirical formula if you can simply use the molecular formula? Well, it turns out that sometimes in the lab, the best you can do is find the empirical formula. Let's look at an example. In this case, an experimenter would want to determine the empirical formula of a compound known to contain only carbon and hydrogen when they experimentally determine the mass of carbon and the mass of hydrogen that were in the compound. Recall that empirical formulas are the simplest ratio of moles. Therefore, we need to convert the grams to moles. In order to do that, we use dimensional analysis, as you have done in the past. We take the grams of carbon and we multiply by 1 mole over 12.01 grams. Remember that the 12.01 grams is the molar mass, which can be found on the periodic table. Grams are on the bottom because we want grams to cancel out. Once we do that, we find the moles of carbon. We repeat a similar procedure, of course using the molar mass of hydrogen, for hydrogen to find the moles of hydrogen. Next, we want to find the empirical formula. Right now, all we have is the moles of each compound. Empirical formula is a ratio of the moles. We need to take a ratio of these two numbers. In order to find a whole number ratio, we need to divide by the smaller number. In this case, the moles of carbon is much smaller than the moles of hydrogen. So we divide both moles by 0.09101 moles in order to determine a ratio. When we do that, of course, the moles of carbon, the ratio is 1 because we divided the same number by itself. In the case of moles of hydrogen, we divide the 0.183 by the 0.09101, and we get a ratio of 2.01. Of course, you know we can't have a 0.01 of a hydrogen. You can have 1 or you can have 2, but you can't have a 0.01. And the reason for this is they're physical things. You can only have integer numbers of them. So we round to the nearest integer, in this case 2. We now have a ratio of moles, but we need to write this as an empirical formula. As an empirical formula, this is CH2. So in this example, the best we could do was determine the empirical formula of the compound. We simply don't have enough experimental information to determine the molecular formula. In this experiment, you're actually going to determine the empirical formula of copper 2 sulfate pentahydrate. You're going to begin by dehydrating the salt, which means removing the water. This is done by heating the salt up. If we know the mass of the salt before we heat it and the mass of the salt after, we can determine the mass of water lost. We can then convert that mass of water to moles of water using the molar mass of water. Next, we're going to determine the mass of copper in the copper 2 sulfate pentahydrate. To do that, we will react the copper sulfate with magnesium metal. In a single replacement reaction, copper metal will form. We will then isolate the copper metal and determine its mass. Once we know its mass, we can find the number of moles. When we know the mass of copper, we can find the mass of sulfate by difference. This poses a problem with this experiment, because if the mass of copper is off, so too will the mass of sulfate, which can cause a cascading error, which may lead to formulas that are far different than CuSO4.5H2O. In this way, you're going to test the accuracy of this experiment. In order to test the precision of the experiment, you're going to do everything 3 times. Said another way, you're going to do 3 trials. You need to do these 3 trials at the same time in order to have enough time to complete the experiment. At the end of the experiment, you will comment on both the accuracy and the precision of your work. In the first part of this experiment, you're going to dehydrate copper 2 sulfate pentahydrate. Before you can do that, you're going to need to get the mass of 3 clean and dry test tubes. You're also going to need to label the test tubes so that you know which is which. It's absolutely essential that these test tubes are clean and dry before you record their mass. You will use the mass of the empty test tube repeatedly when you do your calculations. So if this mass is not accurate, it can cause major problems in your final results. Once you have the mass of 3 clean and dry labeled test tubes, you're going to want to add approximately 0.3 grams of hydrated copper 2 sulfate to each tube. It's very important that you do this experiment in triplicate and that you do the same thing to each of the 3 test tubes at the same time. If you were to do them one at a time, it would take far too long. One nice thing about this dehydration experiment is that the hydrated copper 2 sulfate is a blue color. And when we heat it and form the anhydrous copper 2 sulfate and remove the water molecules, which leave as steam, we form a white compound. So there's a clear color change. You will know the dehydration is complete when you no longer see the blue color. Before dehydrating the copper sulfate, it's important to fill the test tube with the appropriate amount. Because test tubes are in irregular shape, it can be difficult to measure their mass on a balance. In order to measure the mass of a test tube, simply place a beaker onto the balance and tare it. Then insert the empty test tube. Once you have the test tube inside of the balance, you can record its mass. Take the test tube out, add approximately 0.3 grams of copper 2 sulfate, and then simply record the mass again. Make sure you know which test tube is which. Next, we need to light the Bunsen burner. Before lighting the Bunsen burner, it's a good idea to turn it off. The Bunsen burner has 2 components. One for the air, which you want to dial all the way down, and one for the gas, which you want to dial all the way in. Once your Bunsen burner is turned off, you want to simply open the gas about 1.5 turns. Now that your Bunsen burner is ready to go, you're ready to turn on your gas. But before you do that, you want to make sure that your sparker works. In order to make sure the sparker works, you simply want to place your thumb on the arm that moves back and forth, and then swipe it across like this. Once you can get sparks, you're ready to turn on the gas. Now that you have the Bunsen burner ready to go, and the sparker is working, it's time to turn on the gas. To do this, at the bench, simply turn the gas on all the way. Once the gas is on all the way, light it like this. Once you have the Bunsen burner lit, you can see here that I have a flame that's too big. Simply dial in the gas nozzle at the bottom of the Bunsen burner until you have a flame that's approximately 6 to 8 inches tall. It's very important that when you're using a Bunsen burner, you never heat anything with an orange flame. This is because this is incomplete combustion and it will leave soot all over everything. Therefore, we need to add some air to this flame in order to make sure complete combustion is occurring. To do this, you simply turn this nozzle until the appropriate amount of air has been added to the flame. You'll notice that this flame here has a sharp inner cone. The top of this inner cone is the hottest part of the Bunsen burner. Now that we have the flame ready to go, we want to use some test tube tongs. Simply grab the test tube that we're going to heat and gently warm the sides of the test tube. It's very important that you heat up the test tube before you heat the copper sulfate because we're trying to dehydrate the water. If the test tube is cold, we will simply condense the water further up in the test tube. So we want to make sure the entire test tube is good and hot before we start to begin to heat our copper sulfate. Once we've heated the test tube, we then can put the copper sulfate directly into the hot flame. It's now been about a minute of heating the copper sulfate. As you may be able to see, some of the copper sulfate has turned from blue to white. You can also see a small amount of steam leaving the top of the test tube. Every once in a while, it's a good idea to just bring the test tube back down to make sure that you're keeping the test tube nice and hot. It's now been about 2 minutes, and as you can see, the copper sulfate has completely changed color from its original blue color. Copper sulfate is now completely dehydrated. Now we just need to simply cool the test tube down and record the mass of what's remaining. One of the single most dangerous things you're going to use in the lab is the natural gas. This is because if it's left on, it could literally cause an explosion. So it's very important that when you're done using your Bunsen burner, that you turn the gas off at the bench completely. In fact, before you leave the lab, you should triple check that you have turned your gas off to make sure that everyone in the lab is safe. After dehydrating the copper 2 sulfate pentahydrate, you will perform a single replacement reaction and form copper metal so that you can determine the amount of copper in the copper 2 sulfate sample. First, the copper 2 sulfate will be dissolved in water, making an aqueous solution. Then, solid magnesium will be added. The copper 2 sulfate solution will appear as a blue color. The magnesium metal is chunks of shiny metal that you'll cut into small pieces. During the reaction, the magnesium will replace the copper. Magnesium will go from a charge of 0 to a charge of 2+ in magnesium sulfate. Therefore, the magnesium will be oxidized. At the same time, the copper will go from a charge of copper 2+ in copper 2 sulfate to copper metal, which has no charge. Therefore, copper will be reduced. Ultimately, what you will visually see is copper metal will form in the test tube. Once you've dehydrated the copper 2 sulfate, it's now time to precipitate out the copper metal in a single replacement reaction. Before you can do that, we need to dissolve the copper 2 sulfate in water. It's very important that you have a cool test tube before you add water. If you add cold water to a hot test tube, it will crack the glass. So please ensure that the test tube is cold, and then simply add an inch or two of water to the bottom of the tube. You'll notice that the solution instantly turns blue as the copper 2 sulfate is rehydrated. You then want to use a stirring rod to gently swirl the solution until all of the copper 2 sulfate dissolves. After 2 or 3 minutes of stirring, the copper 2 sulfate will dissolve completely. Next, it's time to get the magnesium ready to do the reaction. You're going to need an approximately 4.5 centimeter piece of magnesium to perform the reaction. You want to simply cut your piece of magnesium into 10 equal pieces. Remember that you're doing this reaction in triplicate. We're showing you one example here, but when you're doing the reaction, you want to do everything 3 times. Next, add the magnesium metal to the test tube containing the copper sulfate. And then insert the test tube into a flask or a beaker containing boiling water on a hot plate. You're going to want to let this reaction continue for about 20 minutes. Just as soon as this reaction starts, you can actually see the formation of copper metal as it is reacting with the magnesium. It's now been about 15 minutes, and as you can see, the reaction mixture has changed drastically. Instead of the blue copper 2 sulfate, we now have copper metal precipitated in the bottom of our test tube. Now what we want to do is simply take this out of the boiling water and place it into a cool water bath to cool the solution down before we continue to the next step. Here I've only done one trial with a single test tube, but when you're doing the experiment, it's very important that you do this in triplicate and that you do everything to all 3 test tubes at the same time. If you try to use one test tube and then the next and then the final test tube, the experiment will take far more than 3 hours. It's very important to do all 3 test tubes at one time. After a couple minutes of the test tube cooling in the water bath, it's important we're going to add HCl to the tube to destroy any unreacted magnesium. It's very important that when you actually do this part of the experiment that you're working in the hood. To do this, we're going to simply take our test tube and use 1 dropper full of 5 molar HCl in order to destroy the unreacted magnesium. When you add the HCl to the solution, you'll notice that bubbles immediately begin to form. This is a violently exothermic reaction and the test tube gets very hot. The bubbles are hydrogen gas, so it is very important that this part of the reaction is performed in the hood. After a few minutes, the magnesium will have completely reacted. We now need to centrifuge the test tube to get all of the copper metal at the bottom. Before we can do the centrifuging, we need another test tube with approximately the same volume of water in it to act as a counterweight. Once you have your blank test tube and your test tube with your reaction mixture, you want to place it in the centrifuge. Make sure that you place the 2 test tubes exactly opposite of each other. Close the lid for the centrifuge, set it to 3000 RPMs, and then simply turn on the timer. You want to perform the centrifuge for approximately 1 to 2 minutes. After a few minutes in the centrifuge, you can see that all of the more dense copper metal has collected at the bottom of the tube. Now I want to decant the solution. Decanting means pouring the liquid off of the top of the solid. To do that, you're going to need to use a waste beaker and simply pour the liquid off of the top. It's very important that you pour gently as to not remove any copper metal from the test tube. Once you've decanted the solution, you're going to want to place the test tube in the oven for approximately 15 minutes in an attempt to dry the copper metal. After 15 minutes in the oven, you simply want to record the mass of the copper, metal, and the test tube. Then you can perform your calculations. Once you've collected all of the data, it is important to enter that data into Excel to do the calculations. You can download this template on Blackboard so that all you have to do is fill it out with your data. In this case, we have the mass of the test tube for each of the 4 trials, the mass of the hydrated copper 2 sulfate before we heated it up for the 3 trials, the mass of the test tube after we heated the copper 2 sulfate and dehydrated it, and finally the mass of the test tube and the copper metal after we reacted it with zinc and precipitated the copper metal. We will use these numbers to perform the calculations and determine the empirical formula for each of the trials. In this experiment, there are a large number of calculations to perform in order to determine your empirical formula, and many of these calculations have to be performed repeatedly. Therefore, using Excel will make this much more efficient. It is really important that you learn how to use Excel because it will be useful not only in chemistry, but in your life beyond this course. The Excel template shows all the values that we must calculate in order to determine the empirical formula. The first one we want to do is find the mass of the hydrated copper 2 sulfate for the 3 trials. In order to do that, we simply click on this cell. We type equals so that Excel knows that it needs to do a calculation. We take the mass of the test tube and the hydrated copper 2 sulfate, and we subtract the mass of the test tube. When enter is clicked, it will give us the mass of the hydrated copper 2 sulfate. In order to do this for calculation for trials 2 and trial 3, we simply click on the box we just entered the equation into, grab the bottom right-hand corner, and drag it across. You probably noticed that once you type the equal sign into a cell, by clicking on another cell, Excel will automatically add that cell to part of the calculation. In this example, we subtracted cell B4 from cell B3 by simply typing equals, clicking on B4, then clicking on B3. In order to find the mass of the anhydrous copper 2 sulfate after it has been heated, in this case we again click on this cell, type the equal sign, this time take the mass of the test tube in the anhydrous copper 2 sulfate and subtract the mass of the test tube. We click enter, highlight the cell again, click on the bottom right hand corner, and drag it across. In order to determine the mass of water that was lost, we click on the appropriate cell. Then type the equals sign. Then take the mass of the hydrated copper 2 sulfate and subtract the mass of the anhydrous copper 2 sulfate. The mass that was lost, or the difference between these two masses, is the mass of water. We again highlight the cell and drag it across. In order to determine the number of moles of hydrated copper 2 sulfate, we need to take the grams of hydrated copper 2 sulfate and divide by the molar mass. To do this, we again type the equal sign, take the mass of the hydrated copper 2 sulfate, and divide by 249.69, the molar mass of copper 2 sulfate pentahydrate. Again, once we have the moles, we simply drag it across to get it for the other two trials. You'll notice that in all of these calculations, Excel doesn't give us the correct number of significant figures, very much like a calculator. In this case, we can go ahead and ignore these because these are all intermediate calculations, so we're not going to spend the time to fix them. In order to determine the number of moles of the anhydrous copper 2 sulfate, we do a very similar calculation. This time we put in the equals and we select the mass of the anhydrous copper 2 sulfate. And this time we want to divide by the molar mass of that, which is 159.61. Again, we select the cell and drag it over, and that gives us the moles of copper 2 sulfate for all three trials. We repeat a similar calculation to find the moles of water. This time we click on the cell for water, click on the equal sign, take the mass of water, and divide it by 18.02, which is the molar mass of water. In order to find a mole ratio of water to copper 2 sulfate, we need to divide by the smaller number. You'll notice that in each case, the moles of copper 2 sulfate is a smaller number than the moles of water. In order to find a ratio, we need to take the moles of water and divide by the moles of copper 2 sulfate, which is a smaller number. This should give us a number larger than 1. In order to repeat the calculation, we drag it across as we've done before. This gives us the ratio of the moles of water to the moles of copper 2 sulfate. You'll notice that experimentally, for the first trial, we found about 5 moles of water for every mole of copper 2 sulfate. For the second and the third trials, we were around 4. This is getting at the empirical formula. So there are about 4 or 5 waters per mole of copper 2 sulfate. A little bit later on, we'll find the average of these numbers, and we'll calculate the precision and the accuracy of our results. However, before we get to the averages, we need to find the ratio of copper to sulfate. To do that, we need to begin by finding the mass of the copper that we precipitated. In order to do this, we need to do a subtraction. In this case, we want to take the mass of the test tube and the copper metal and subtract the mass of the test tube. This will give us the mass of copper metal that we formed when we reacted the copper 2 sulfate with zinc. If we drag this cell across, we will get the mass of copper for each of our trials. Next, we want to find the mass of sulfate, which we can do by difference. To do this, we want to take the mass of the anhydrous copper sulfate and subtract the mass of copper that was in that copper 2 sulfate. This will give us the mass of sulfate that was in the original sample by difference. Again, we can do this calculation for all three trials by simply dragging it across. To determine the empirical formula, we need a ratio of moles, not a ratio of masses. So we need to convert the grams of copper to moles. To do this, we take the mass of copper and we divide by the molar mass of copper, which is 63.55 grams per mole. After repeating this calculation for all of the three trials, we want to find the moles of sulfate. To do that, we again type equals, take the grams of sulfate, and divide by the molar mass of sulfate, which is 96.06 grams per mole. We can again drag it across, and now we have the moles of copper and the moles of sulfate. Next, we'll find the ratio. To determine the ratio, we need to divide by the smaller number. You can see here that in all cases, the moles of copper is smaller than the moles of sulfate. So to find the ratio, we take the moles of sulfate and divide by the moles of copper. Dragging across, you'll see that all numbers are greater than 1. Here you can see that in the first trial, we got about 1 sulfate for every 1 copper, which is correct for copper 2 sulfate pentahydrate. However, in trials 2 and 3, we found closer to 2 moles of sulfate for every mole of copper, which would make it copper 4 sulfate. This is clearly not correct. This occurs because when we find the mass of copper, if it is a little bit off, and then we find the mass of sulfate by difference, because we simply subtract the mass of the original copper 2 sulfate that we had, and we subtract out the mass of copper that we found, for any amount that the mass of copper is off, the mass of sulfate is going to be off that much more because we find them by difference. Therefore, this is a major experimental flaw in the experimental design. So now we're going to test to see the accuracy and the precision of these experimental results. It's entirely possible that when you do this lab, you're not going to find the empirical formula for all 3 trials to be copper 2 sulfate pentahydrate. In this case, we have found things that are quite a bit different. In order to do the statistical analysis, we want to start by finding the average mole ratio of water to copper 2 sulfate. Notice that we have the 3 individual mole ratios here. In order to find the average, Excel has a pre-canned function. To use it, type in average, open a parentheses, and highlight the data that you wish to average. You don't have to, but you can close the parentheses at the end and then hit enter. This is the average mole ratio of water to copper 2 sulfate. Excel also has a pre-canned standard deviation function. To find the standard deviation of these 3 values, we type in equals STDEV, again open a parentheses, and select the 3 data points. This will give us the standard deviation of these 3 values. Notice here I will not close the parentheses because it's not entirely necessary. When you click enter, you get the standard deviation. Next, we want to calculate the relative standard deviation because that's what we will use to determine the precision, or how close the values are to each other, or how reproducible the experiment is. To find the relative standard deviation, we take the standard deviation, we divide it by the average, and because we want it in parts per thousand, we multiply that value by 1,000. Notice here that the relative standard deviation is 143.8 parts per thousand. This is about 15%. This means there is quite a lot of variation in these values, which you could tell just by looking at them. This means that this particular experiment is not particularly precise. In order to determine the accuracy of this particular part of the experiment, we need to compare it to the moles of water that we expected to find, which in this case is 5. To do the math, we take the accepted value, 5. We subtract the average experimental value for the moles of water to the moles of copper 2 sulfate, which is 4.3 in cell B25. And then we divide by the accepted value, which is 5. Because we want the percent error as a percentage, we multiply this entire value by 100. When we do this, we find that the percent error is about 14%. Again, there's quite a bit of error, just like there's quite a bit of imprecision in our experimental work. We need to repeat the accuracy and the precision calculations for the ratio of sulfate to copper. We do this in the exact same way. We start by determining the average ratio of sulfate to copper, again using the pre-canned average function. We open the parentheses, select the data, and hit enter. Next, we find the standard deviation by using STDEV, opening the parentheses and selecting the data. To find the relative standard deviation, we take the standard deviation, we divide by the average, and because we want it in parts per thousand, we multiply by 1,000. Here, you can see that this relative standard deviation is even greater than the relative standard deviation for the ratio of water to copper. This means that there is even less precision in the ratio of copper to sulfate than there is of water to copper to sulfate. We want to calculate the percent error to look at the accuracy of this part of the experiment. In order to do that, we need to subtract the accepted value and the value that we found. In this case, the accepted value is 1 mole of copper for every 1 mole of sulfate. Because we got an average ratio that is greater than 1, we want to actually subtract the 1.62 minus 1. This is because we want to make sure that the percent error is a positive value. Another way you could do this is to take the absolute value of the subtraction to ensure you always get a positive number. Next, we want to divide by the accepted value, which is 1 to 1. So we divide by 1 and multiply by 100 to get a percentage. You can see that this portion of the experiment is even less accurate than the portion of the experiment where we compared the moles of water to the moles of copper to sulfate. Now we can look at the experimental empirical formula on average for this compound. What we found was it's Cu SO42, rounding to the nearest whole number, dot 4 H2O, again rounding to the nearest whole number. If we compare this to the known formula, copper, 1 sulfate, 5 waters, you can see that we're quite a bit off. We also know that the precision isn't great because we got an RSD of 143 for water to copper sulfate and an RSD of 343 for sulfate to copper. So both the accuracy and the precision are not great in this particular experiment. Again, the accuracy is calculated by the percentage error, which are quite high, but very high in the case of sulfate to copper. So the experiment didn't work perfectly. This is most likely because one mass is based on another. So when we calculate the mass of sulfate, we calculate it by difference. If this tiny masses, 74 milligrams in this case of copper, is even a little bit off, it's going to also throw off the mass of sulfate. One way that we could do this experiment better is to start with a lot more copper sulfate pentahydrate at the beginning. Instead of starting with 0.3 grams, maybe we want to start with 10 or 20 grams of the compound. Then small differences in mass will cause less difference and cause, therefore, a smaller error. However, in this particular experiment, due to time constraints and not wanting to use large amounts of the compound, we did go ahead and only use around 0.3 grams. Make sure that in your lab experiment, you comment on the accuracy and precision of your data. Remember again that accuracy is based on the percent error and precision is based on the RST. Finally, I want to discuss setting up your Excel sheet before you come to lab. Notice that if I delete the experimental data here, all of these calculations are still programmed into Excel. When I type in the experimental data, it will calculate all of this for me before I even come to lab. The only thing that you don't have before lab is the actual experimental data. I would strongly recommend that you watch this section of the video again after downloading a copy of this template from Blackboard. Then enter all of your calculations into Excel as you go. You can use the numbers that I had up here to make sure that all the numbers match as you go. Therefore, you will have your entire Excel sheet ready to go before you come in. Enter the experimental data, and you will know everything without having to do the calculations during the precious lab time.